Hi everyone. How do you find the x-intercepts on the graph of y equals f of x? Well, in general, how do you find x-intercepts in the xy plane? You set y equal to 0. You set y equal to 0. You set the function rule equal to 0. And you find the real solutions of this equation. The real solutions of this equation are the real zeros or roots of f. Bear in mind that the number 0 itself may or may not be a 0, so the term 0 might be misleading, but then again, the term root can also be misleading as well. Bottom line, we want the real solutions for y, or f of x, equal to 0. Now, to find the y-intercept, that's usually easier. To find a y-intercept, we plug x equals 0. We plug in x equals 0. Which means that we're evaluating f of 0. And we identify the corresponding point, 0, f of 0. If 0 is not in the domain, then there is no y-intercept. Example. Basically, find the x-intercepts of the graph of y equals f of x, where f of x is x squared minus 9. I basically want to consider the graph of y equals x squared minus 9. So how do we find x-intercepts? We set y, or this function rule, equal to 0. We're solving an equation. You set x squared minus 9 equals 0. Solve the equation. There's no x term, so we can add 9 to both sides and use the square root method. X squared equals 9, and then x equals plus or minus, don't forget the plus or minus, 3. So 3 and negative 3 are the real zeros or roots of this function. Therefore, the x-intercepts are at the points 3, 0 and negative 3, 0. Remember that we normally write x-intercepts as ordered pairs. And again, to find x-intercepts, we have to solve an equation. We solve the equation y, or f of x, equal to 0. So here's the graph of y equals x squared minus 9. If we zoom in a bit, we can see that the x-intercepts are going to be at negative 3, 0 and at 3, 0. Those are our x-intercepts, where the graph hits the x-axis. Now, where's the y-intercept? Well, that's usually easier, because to find a y-intercept, that involves evaluating at 0. So you're basically finding f of 0. When you plug in 0 for x, here, you get y equals negative 9. So that means that the point 0, negative 9 is the y-intercept. So once again, x-intercepts tend to be harder to find because you have to solve an equation. Y-intercepts tend to be easier to find because that just involves basically evaluating at 0. Assuming that these intercepts exist. You might have graphs where neither will exist. But for here, we have two x-intercepts. Our y-intercept will be at the point 0, negative 9. All right. Here's the graph once again. X-intercepts here in black, y-intercept in red here. Let's say we have radicals involved. So here's the idea. The root, in general, the nth root of g of x equals 0, if and only if g of x, the radicand itself, is 0. So basically, to find the zeros of a radical is quite easy. You can just remove the radical and consider the zeros of the radicand. The zeros of a radical are just the zeros of the radicand. So for example, if I ask you to find the x-intercepts for y equals root x squared minus 9, well, really, it boils down to finding the real zeros of just the radicand, x squared minus 9. And we've done that. We already found that the real zeros were 3 and negative 3, so we get the same x-intercepts as before. Although the graph we're talking about, y equals the square root of x squared minus 9, looks a bit different. Notice the graph disappears in the middle here. Why is that? Why does the graph disappear here? because the values of x in here are not in the what of the function. They're not in the domain of the function. The values of x in here, like 0, they're going to make the radicand negative, like -9. And that's going to be illegal. We want to keep things real. Look at the impact that the square root operator has on x squared minus 9. So notice here that although we do get a flattening out here and out here, as you might expect, actually we get a steepening as we approach the two x-intercepts. And the black graph, the actual square root graph, the black graph shares the same x-intercepts as the red graph. So again, the point I was making before, the x-intercepts don't change whether you apply the square root here or not. The domain could change here. These values are around 0 or no longer in the domain. But the x-intercepts stay the same, whether there's a square root there or not. What if we have a fraction? Well, in general, when does a fraction equal 0? When which part equals 0? A fraction is equal to 0 when the top part is equal to 0, but the bottom part is not. Otherwise, you have a domain problem. Remember, if you're dividing by 0, then that's a domain problem, and this thing is undefined. 0 over 0 is undefined. 0 over any other real number is 0. Okay, so how do we find the x-intercepts in this case, where f of x equals a numerator over a denominator? To find the zeros of a fraction, you want to find the zeros of the numerator, but they have to be in the domain of the overall thing. So we want to find, so that where are the zeros of f? They're the zeros of the numerator, but they have to stay in the domain of f. In particular, they cannot be zeros of the denominator. So in a typical setup, you want to find values for x that will make the top 0, but not the bottom. Although there could be other domain issues, like if you're dealing with tangent of x or something. But for a typical algebraic function, you get zeros if the top is 0 and the bottom is not. All right, so let's find the zeros of f, where f of x equals the fraction x squared minus 9 over x plus 7. So when does this equal 0? We're finding x-intercepts. When does this y guy equal 0? When the top is 0 and the bottom is not. When the top is 0 and the bottom is not. So we want to know when x squared minus 9 equals 0. Well, we've answered this question several times before. This fraction equals 0 if and only if the top, x squared minus 9 equals 0. And by the way, when the bottom is not. And the bottom is only 0 when x is -7. So if we get -7, we better reject it. But when you solve x squared minus 9 equals 0, we know once again that the only real solutions are 3 and -3. -7 is not in the mix. If it were, we'd reject them. And once again, we have the same x-intercepts as before, at 3, 0 and -3, 0. Here's the graph. So parentheses, use parentheses, x squared minus 9 over parentheses x plus 7. This is f of x. All right. And notice, once again, we have the same x-intercepts. We have the same x-intercepts at 3, 0 and at at 3, 0 over here and at -3, 0 over here. By the way, these points in gray, we have the y-intercept here and we have a minimum point over here. Interesting. All right. To find the y-intercept, plug in x equals 0, you get -9/7. So the y-coordinate here is about -9/7. If you don't believe me, 0, -9/7, boom, the y-intercept. There you go, y-intercept. That was easier. All right. This problem is surprisingly harder. If f of x equals the fraction x squared minus 9 over x minus 3, again, let's find the x-intercepts. I basically want to find the real zeros of this fraction over here. Once again, I need to make the top 0, but not the bottom. For an easy rational expression like this, it's as straightforward as that. We want to make the top 0, but not the bottom. All right. Well, here's the deal. When you solve x squared minus 9 equals 0, you get two tentative solutions. Okay, you get two tentative solutions, 3 and negative 3. But wait a minute, 3 makes the denominator 0. So you can't have that. 3 makes the denominator 0, you can't have that. Negative 3 is the only real solution to this equals 0. Negative 3 is the only real 0 for this. So negative 3 comma 0 is the only x-intercept. Here's the graph. I'll do a new thing here. Parentheses, x squared minus 9 all over x minus 3. Oh, look at this. Look at this. We get a line. Really, there should be a hole over here at 3 comma 6. So Desmos is being a little naughty. We'll talk about this in chapter 2. But this is really going to, so the graph of y equals this is going to be a slanted line where there should be a hole at 3 comma 6. Right. But we really basically get a line. Think about that. Think about why that is. We only have one x-intercept at negative 3 comma 0. That's our only x-intercept. And once again, why is that? Let's trace the logic. When does this thing equal 0? Okay, when does f of x equal 0? When, not 6, 0. It's 0 if and only if x squared minus 9 equals 0 and x minus 3 is not 0. X minus 3 is not 0. I'll put that in green. X minus 3 is not 0. Or more simply, x is not 3. X cannot be 3. So from the purple here, x squared minus 9 equals 0, we get, oh, so I'll put a parenthesis here. X could be 3, or x could be negative 3, as we've seen a million times before. These are the real zeros for x squared minus 9. But wait, and, hey, wait a minute, there's a restriction here. X cannot be 3. It's a restriction that's relevant. The restriction up here that x couldn't be negative 7, that turned out not to be relevant in the end. Here, oh, this is relevant. This tells us that we have to reject x equals 3. We have to reject x equals 3, like Taylor Swift rejects a boyfriend. All right. We're left with x equals negative 3. All right. So negative 3 is the only real 0 for this guy here, the fraction. All right. So we only have one x-intercept, negative 3 comma 0. All right. Next up, this is our monster for the day. Find the t-intercepts for the graph of y equals this thing. The key thing is find the real zeros or roots for this. We'll do that next time.